Hi, this is Ms. Gilchrist, and we're going to record the lesson for Thursday, May 13th. The objective of this lesson is to give you an introduction to the next function that we're going to study, which is exponential function. And what I'm going to do is compare it with one you should have studied in Math Models A, linear. So, or hopefully you have some experience with linear. We've done just a tiny bit in this class. Mainly we've been working with quadratic, so we're going to shift over there. So I'll talk a little bit more, but let me go ahead and start this thing where I share the screen. And we're not going to start here. We're going to start here with this little experiment. Now I do like in class that it's kind of an active thing, and it's one of my favorite days. And we cut pieces of paper and we do this kind of thing, and I wish we could do it, but I'm just going to give you a flavor of it, of how we're going to look at the difference between linear and exponential. Now again, this is an introductory lesson, and really there's nothing for you to turn in today with this one except for the daily question, which is going back and reviewing some things we did with transformations. So right now, just take note, well, just listen and kind of get the idea behind it. And we'll get to the part where you're going to actually take notes. You don't need to take notes over any of this right now. Just kind of take it in and look at the visuals, and hopefully they'll tell a story. My idea is that these visuals will tell a little story about the linear and the exponential, and then we'll get to the next, one step at a time. So this is just step one. So what I want to do is explore the idea, and this is kind of experiment number one, or example number one, and we're going to fill in a table, and then we're going to do a bar graph to represent these two situations. So in this situation, I'm going to start with 1, and then I'm going to add 2 each time. And then over here, I'm going to start with 1, but then I'm going to multiply by 2 each time. So we're starting with the same number, and here we're going to add 2, and then we're going to multiply by 2. And this just bothers me. It shouldn't, but it does. Okay, so let's get going. I am going to do the table first. And let's see, I've got my table, and I'm going to edit it. So at 0, that's the starting point. So I'm going to start with 1, and that's my starting number. Again, to look at the starting number on a table, the X is 0. 0 marks the starting point. And what I'm going to do as I go down is that I am going to add 2. So I start with 1, and then I'm going to add 2, so I get 3. And then I'm going to add, I have 3, and I'm going to add 2, I get 5. And then 7, then 9, then 11. As I go down each time on this side, and this is where the actions happen from here, add 2, add 2, add 2, add 2, add 2. And again, the 0 marks the starting point. So I think I found this works best. I'm going to start with 1 square. Why is that marking? Oh, maybe I need something darker. Then I'm going to add 2. I have to use a different thing that's hard to see. I thought I had found the one that's you could see. So there's my first one. And then I'm going to add 2 more. And I'm going to add 2 more. I'm going to add 2 more and add 2 more. I kind of messed up that one, but hopefully you get the idea. Now over here, what I'm going to do is I'm going to fill out the table, and then we'll do a chart. So the 0 is acting as the starting point. So I'm going to start with 1, And then when I go to the next one, what I'm going to do is multiply. So 1 times 2, and then now I have a 2, so I'm going to 2 times 2, and then I've got a 4 times 2, now I have an 8, and then as I go down, I'm going to keep multiplying by 2. Those numbers got a little bit hard to fit in my little graph. Let's see if I can make that a little bit easier. So, this is, let me do this one in red. So the starting, it starts at 1, so I have 1 square, and then I have 2 squares, and then I have 4 squares, then 8 squares, and now it gets tough to, I'm going to estimate this, but it's twice as big, so it's somewhere like that much. This one's 8 and this is 16. That's probably a little bit more up here. And then the next one is 32. So it's off the chart there. So this is what I'm adding to, and this is what I'm multiplying to. And right here, we pretty much have the example that I want to show you. What I want to do is connect the corners. So this starts at 1, and then if I connect the corners, I end up with basically a straight line. But if I connect the corners here, it's going to scoop up. It's curving. It won't be a straight line. It's going to have to curve. So this is adding 2 every time. And this is multiplying by 2 every time. Well, guess which one is linear? So we've got this here is going to be our linear because it's forming, and this, if I connect the corners, it would be a straight line. And what happens here, this one is called exponential. And I'm trying to write it. Yes, exponential. And this is the exponential function. Now this is only a piece of the curve. We're going to talk about more of that in just a minute, but let's do another example. Here we're going to start, on this one I'm going to start with 16, and this one I'm going to start with 32. So we're not exactly starting with the same number, but you'll still be able to see what I want you to see here. So here, again, my starting number is 16. And my rule is that I'm going to subtract 2 every time. So then I'm going to get 14. Then I'm going to get 12. Keep subtracting 2. That one's 10. Then 8. And then subtract 2 again, I get 16. Is it still letting me do that? I mean 6. So I'm going to start with 16. Let me get to the marker. So let's see, 2, 4, 6, 8, 10. Of course, my cursor is going to do what my cursor does. It's hard to see these little 2, 4, 6, 8, 10. 12, 14, 16. So the first one's 16 squares, and I'm going to subtract 2, so that's 14 squares. I'm going to subtract 2, that's 12. subtract 2, 10, 8, 6, 4, 2. I could keep going. Every time I'm subtracting 2. And again, notice what's happening here is that if I connect the corners, that is a straight line. Now I can't draw it perfectly straight on here, but this is another example of linear. It's a straight line, and I'm going over and over and subtracting. So the difference is this line is going down and this line is going up. When you add and add and add, it increases. This one is also increasing. It's going up, but it's going up at a much quicker rate. This one has a constant rate. It goes up by 2. And the rate of change, that's another way to say slope. So when I can count this, I'm counting over here, rise over run, 2 over 1, 2 over 1, 2 over 1. And it's constantly the same on a line. It's always the same ratio of rise to run. But over here, the ratio is going to change. It will not stay the same. This is 1 to 1. And then this is 3 to 1. And then this is like 4 to 1. And then 12. I'm going to go up 4 squares here. I'm going to go up 8 squares here. You know, it's always changing. So this has a constant rate of change. And this one, the rate of change changes. It's just not the same. It's increasing, the gap is getting bigger and bigger and bigger. And this one is decreasing. It's going down, and it's always going down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. Constant. It's a constant rate of change. And let's take a look at this one. Now, I have got a different starting number. I've got to start with 32. And this time I'm going to divide by 2. Now, another way to think of divide by 2, let me just talk about these words. Another way to think of dividing by 2 is taking half of something. This is kind of, and there's this line here that means divide. So I'm dividing by 2. So you can think of it, anytime it says divide by 2, it's a half, or anytime it's a half, it's like dividing into 2 parts. The denominator, that number at the bottom, tells you how many parts to divide it into. So I'm going to take and start with my 32. Let's see if I get it here. And then I'm going to divide it into 2. So that means I have now 16. Make that still wider so I can see that. So I start with 32, then I'm going to 16, and then down here we're going to divide that into 2. So now it's 8. Then I'm going to divide that into 2. It's 4. I'll divide that into 2. It's 2. And if I went one further, I would get 1. And then if I went further, I would get, if I took 1 and divided it in half, I'd get a half. And if you take a half and divide it in half, you get a fourth. And so we keep getting these really tiny numbers. So now we're going to see a little bit more of the action. So let me do a kind of graph. So I'm not going to count 32, but I know it's kind of like way up here. And so it's like here. And then about half of that would be 16. And then half of that would be 8. Then half of that would be 4. And then 2. And then 1. And then like half. And then half of a half. And then half of a half of a half. And it gets on and on. I did make that line a little bit longer. There's my cursor. So here, this one starts really, really high, and then it starts getting smaller and smaller. And so let's see if we can get this thing where I am going to connect the corners. And to get the corners, now you can see a little bit better how it's curving. And it's going to keep getting smaller and smaller and smaller as I get closer out here. So it's going to keep getting, like, you know, you take a half, and then you take a half of that, you take a half of that, and it's getting so tiny that I can't show you with my fingers, but it is like, it's half of a, and then you take half of that and then half of that, and you need a microscope to keep slicing that little sliver into halves. But that's happening here. And so this one scoops way down. So both of these are decreasing. This is the one that is the linear. So this is the example of a linear function. And here we have the exponential function. So we've got these partner operations. Let me get this. And I've got more examples planned, but I may just go ahead and use these. So these are both decreasing. This is linear, but this is exponential. This is a straight line, and this is a curved line. This over here on the left, it's a constant rate of change. It's constantly down 2 over 1, down 2 over 1. And rate of change is the same thing as slope. Here, the first time it's down 16 over 1, then it's down 8 over 1, then 4 over 1, then 2 over 1. It's getting the rate of change, or the slope is changing every time. Between 2 points, it's never the same. So with linear, this example is adding, and this example is subtracting. Add and subtract are like they're flip sides of the same coin. They're partners. They're very, very much connected. And also here with the linear, for the increasing, I'm multiplying every time. And as you multiply, it's going to get bigger and bigger and bigger. But the operation that's the partner with multiply is divide. They're just flip sides of the same basic operation. Oh, and I went too far. And so when you divide, it decreases. It's going down, down, down. So that is that's the shortcut version of our exploration of just showing how it's going to increase and decrease in different ways. Let me go ahead and just use these two examples, and I want to start to talk about the equations that I'm going to use. And so I want to write some equations for this one. And what I'm going to do with this equation, I'm going to start with the way I like to start as y equals. Of course, it could be f of x equals if we're using function notation. And what did this one start with? Over here on this one, I started with a 1, so I'm going to start with a 1. And then I'm going to add 2 each time. And at each x, I'm just going to, each time I go to a new x, I'm going to add 2. So I'm adding 2, adding 2, adding 2. And when you add over and over, that's the same thing as multiplication. And I'll talk about that in a minute. Now for this one, I'm going to say y equals, and I'm starting with 1. And then my rule was, on this one, is to multiply by 2 each time. Now here what I'm doing is I'm multiplying over and over and over. And if you multiply and multiply and multiply, to show that you're multiplying repeatedly, we use an exponent. And let's just talk about that for a minute. Let me get a new screen. So think about this. If I say 2 plus 2 plus 2 plus 2 plus 2 plus 2, another way to write that is 2 times 5. So this is going back to, and you may not have given it much thought at all since, maybe 3rd grade or whenever you started learning multiplication. But multiplication is just adding over and over. And so if I add 2 5 times, it's 2 times 5. But if I do 2 times 2, and I multiply it over and over, and let's just go ahead and do this 5 times. And I say, instead of adding 2 over and over, I multiply by 2 over and over. Another way to write this, 2 times 2 times 2 times 2 times 2, is 2 to the 5th power. So that's another dynamic here, is that with linear, we're adding over and over, which means in the formula you're going to see multiplication. And so that's here, where the 2x is 2 multiplied by however many times. Are you going to do it 1 time, 2 times, however many times you're going to add 2? If this is when I've added 2 5 times. This is when I've added 2 2 times. And then this one is I'm multiplying. And so I use the exponent to show that I'm multiplying however many times. The x will say how many times you multiply. This x tells you how many times you add. So this phrase is a multiplication phrase, and this phrase is using exponents. But what we're doing is the same thing. Now the formula, if you've studied linear before, linear, oops, I don't want to use that marker. Linear, the first equation you usually learn is mx plus b. And all I'm doing is switching that around. I'm saying y equals b plus mx. So I'm switching the mx and the b. But it's addition, so it doesn't matter. Like 2 plus 3 and 3 plus 2 mean the same thing. It's the same thing. So b is the starting amount. The rate, this rate of change is 2, which is also called the slope, or the rise over run. And the x just says how many times you're doing that. So we're thinking of it, I'm talking about it in terms of b plus mx instead of mx plus b. And here, what the formula that we're going to use for this one, the basic formula is y equals a times b to the x. And usually you'll see, well, you can see abx, or you might just see the dot for multiplication. A is the starting amount. So the starting amount here is 1, and b is the multiplier. It's the common ratio. It's called the common ratio. And so here a is 1 and b is 2, because we started with 1 and we're multiplying by 2 each time. You can see the the starting amount right here. It's a point. You can find it on the y-intercept. So it's also the y-intercept. The y-intercept is 1. Here, the b, and I use a different letter, but it's the one without the x. It's just the number by itself. It's also the y-intercept right there. That's number 1. So let's look at the second set. And the idea now is what I want to look at is writing the equation. So I'm going to start here. Y equals And what number did I start with here? The starting number. Now, if I counted up on the y-axis, it would be right here. I could find it there. Or you can find it in your graph, in your table. If they have a table, you can find the starting amount if you look for the 0 where the x is. So this starting amount is 16. And then what I'm doing is I'm subtracting 2 each time. So this is where I start at. I'm starting at 16 and subtracting 2 every time. So that would be the formula for this linear function that's represented here. Now to do this exponential, we'll say y equals, and we're going to put our starting number. And again, if you're on a graph, you can look at the starting number, and I guesstimated this one, so we'll just call that 32. And if you're in the table, you look for the 0 where the x is. That's the starting number. So this one starts at 32. And I'm dividing by 2 every time. Now the trick is with these equations, they're always going to give the equation in terms of a multiplication problem. So I'm going to say times 1/2. This is the other way to express that I'm dividing by 2, is to use a fraction. And I'm doing this over and over, so the exponent would go over here. This is the starting amount, and this is the common ratio. The first number is called A, the second number is called B. In linear, this is called the B, and this is the M. But we're going to focus right now, the last few weeks, on learning this equation, A times B to the X. And that was our formula. There's another formula that expands on this when we're using percents, but the beginning one, and just for a little while, we're just going to talk about A times B to the X. And again, the first number is the starting number, and then what you multiply is the second number. Now I'm going to show you one more thing on this one here. Anytime the starting number is 1, you might end up with an invisible 1. So think about what happens if you take a number and multiply by 1. 3 times 1, 3. 5 times 1, 5. 6 times 1, 6. So when you multiply by 1, you just get that number back. So it can be invisible. So a lot of times you'll see if the starting amount is 1, it will be invisible. And that this formula for this one, 1 times 2 to the x, would actually be written y equals 2 to the x. And but for exponentials, there's always a starting amount. If you don't see 2 numbers, then the A is 1, pretty much. So let me do just another bit of review. And again, none of that you really needed to copy or take notes on. Now when we get to this second part, this is where you may want to make the notes. This is the first part. It's just kind of get some idea. You may want to come back and watch this another time. So what we're doing is we're chapter 3, and this is kind of the first lesson, and the title is exponential functions. And one thing we noticed so far is that linear graphs is a straight line, and exponential is this curve. Now, both of these are the positive increasing versions. There are decreasing versions. For linear, you could have a line go down. For exponential, you could have a line that went that way, that started high and went down low and then scooped. Or it can start low and then scoop up high. If it goes up, it's from adding, repeated addition. If it goes down, it's repeated subtraction. If it goes up, it's repeatedly multiplying. If it's going down, it's repeated division. Or remember, you'll see a fraction, like the kind of fraction that's less than 1. 1/2, 1/3, 1/4. Almost always it's going to be 1 something with these functions. But definitely, so we'll talk a little bit more of that. But these are some things we noticed so far. Here's another, let me get to my other slide. So here again is, oh, and it's going to keep those marks on there. I'm using a new thing. Here's written out. And again, these are some notes you may want to take down. The linear graph is a straight line, and we have 2 different versions of the formula. It's really the same thing, b plus mx or mx plus b. It's just switching those places. And what we're doing is we're adding or subtracting each time. And when you add over and over, you subtract over, basically you're doing multiplication. Another thing we noticed about that straight line is that the slope or the rate of change was constant. It was always the same. And that is the M. The rate of change, no, I want, there we go. It's the coefficient of X. So the rate of change is here on this one and here on this one. And so it's the same number. And it's the same amount. And the B is the starting amount or the y-intercept. So on this one, B is y-intercept or the starting amount. For exponential, the differences, here were the differences. It's that it graphed as a steep curve. It can either go down and up or low and down. And we're multiplying or dividing each time. And when we show over and over that we're multiplying, that's when we use an exponent. And the exponent can be written 2 ways. As a little number raised up high, and in your format tools, in most word processing, that's called a superscript, if you need that little 5. Or you can use, if you use it as a regular size number, then you use this little hash mark that's called a caret, that on most keyboards is on the number 6. To type that out, you use the shift key. And the rate of change or the slope is always changing. It's not constant. This is constant, this is not constant. And the main formula that we're going to use is y equals a times b to the x. And then I'm just going to stop, explore just a little bit more with this formula, a times b to the x. And again, you can pause and stop as you need to make notes. I'm going to go on to the next slide. We've just got a little bit more that we're going to do right now. And I have to clean this up. Okay. So this is what we're going to be working with, is this formula. And the formula that we're working with today is this one, a times b to the x. This is the starting amount, and this is the rate, or it's better to, let me add something here. More often than not, it's called the common ratio. Now so like if it doubles, because we had that one where each time, let's say we're going to multiply by 2 every time, that's another word for that is doubling. If they're multiplying by 3 every time, they may call that tripling, quadrupling times 4, quintupling times 5. We rarely use those words after that. And this is one version of that. Now there is a more complicated version where the b value comes from a percent. And in particular, oh, never mind that. I'm trying to, oh, forget this. I'm going to do this here. If they give you a percent of increase, then we're going to work with a different formula. And I'm going to talk a little bit more about that either in a video for Friday or Monday. Please do your best to watch each video each day. This is the last full week of instruction. We're in the final countdown. This is not a time to save it up and do it on the weekend. As best you can, take it in each day. Then that's the way I've got it paced out, where it should make more sense to your brain to take it step by step. You know, and bottom line, then there's not going to be some time to make things up, because we're coming to the end of the course. Basically, I want you to be through with all your daily work and everything by next Friday, Friday the 21st. No makeup work for the last week. Get your makeup in by Friday the 21st. Saturday, you know, maybe that weekend, but by the 24th, we can't be doing any makeup work. It's too late. It's too close to the end. So just keep that in mind. That was really what I wanted to kind of introduce for you today, how to use those formulas. And, you know, go back and watch it as you need to. I think this will be a good video. Actually, you know, once even as you go, you may want to watch this one again as we go and study the other parts of it. But I'll be reviewing as we go as best I can for you as well. So thank you for watching and taking the time to take that in and take those notes for yourself. Keep there for yourself. Really, I don't need to see them. I just need to trust that you've got them for yourself. And we'll take it a step further on Friday and do, like, again, one day at a time, one step at a time, and do your daily question. And I've tried to include on that daily question lots of information and instructions on how to do each piece, and soak it in, learn from the things that I'm writing and telling you, and let them kind of sink into your brain. Write them out if you need to. Make yourself those notes that click it for your brain. And I will see you in some kind of a video for Friday.